Hello students, the next video is I'm going to explain you the theorem of this Heine borel theorem. So what does it say? It says that every closed and bounded subset of Rn is compact. So if S is closed and bounded subset of Rn, then S must be compact. Or in other words, they can ask you to prove that assume F is an open covering of a closed and bounded set S in Rn, then a finite subcollection of F also covers A. So means that what you have to show that there exists, if F here is an open covering of this set, if F is an open covering of this set S, if F is an open covering of set S, then there exists a finite subcollection of this which still covers A. So either this or this statement, the proof will be the same. So what is the proof here? So F here is an open covering of let F be an open covering of S subset of Rn. What we need to show is that what is S here? S is closed and bounded set, bounded subset of Rn. What we have to show that there exists a finite subcollection of F which still covers F. So by Lindelof theorem, the preceding theorem that I've just explained to you is by Lindelof covering theorem, there exists a countable subcollection of this set F, say I1, I2, dash dash, which covers S. That is, S, according to definition of open covers, S is contained in union of I alpha belong to indexing set I, or lambda is an indexing set. Now if this collection here, this one is finite, then the proof is complete. Or we can say that the result is proof, that is S is compact. But suppose F here, this cover is not finite, this collection. So if this collection, or we can say that if F is finite, F here is this collection of open covers of S. If F is finite, then the proof is, hence the proof, Now if suppose this cover is not finite, what we shall do is that we shall show that we are going to prove that even if it is not finite also, we will be able to find a finite member of this collection. Say we will be able to find a finite collection of this member, say I1, I2, dash dash, which still cover S. That is, S is compact. So which means that we are going to show that even if this collection or this cover that is not finite, we are going to show that a finite number of them still cover S, that is, S is compact. So consider for m greater than equal to 1, the finite union, this one Sm equal to union of Ik, where k varies from 1 to m. So for m greater than equal to 1, consider this finite union, which means that for m is equal to 1, S1 is equal to I1 itself. And what is S2? S2 is equal to union of I, k, where k here varies from 1 to 2, which means that I1 union I2. And for m is equal to, this is for m equal to 2, m equal to 1. For m is equal to 3, it will be, S3 will be equal to I1 union I2 union I3. And in general, if Sm here will be equal to I1 union I2 union dash dash union Im. So here this Sm being the union of open set, because each of these I1, I2 dash dash Im, they are all open set. I1, I2, they are open set. So therefore Sm being a finite union of open set is again open. Now we shall show that for some value of m, for some value of m, Sm union of Sm covers S. Means for some value of m, okay, we will show that the union of those Sm, which is for some value of m, union of Sm will covers S. That is, S is compact. And for this purpose, we consider the complement, this one. You consider the complement, consider Rn minus Sm. So since Sm is open, as we have seen here, being the finite union of open set, Sm is open. So the complement of Sm, that is Rm minus Sm, will be closed. Okay, by definition of closed set, a set is closed if its complement is open. Now consider this set which is closed. Now define a countable collection. Say define a countable collection Q1, Q2, dash dash as follows. Okay, you set Q1 is equal to set S itself, but for m greater than 1, Qm is defined as S intersection of Rn minus Sm. Okay, so we define this countable collection Q1, Q2 as follows, with Q1 being equal to set S itself, but for m greater than 1, we define Qm to be S intersection of Rn. That is, Q2 here will be equal to S intersection of Rn minus S2 and so on. That is, this Qm for m greater than 1, Qm consists all those elements of S which does not belong to, which, or we can say that which lies outside Sm. Okay, so Qm will consist of all those elements of set S which lies outside Sm. Now if we can show that for some m, if we can show that for some m, Qm is empty, then we shall show that for this value of m, no point of S will lies outside Sm. That is, we have shown that then we would have shown that S for some m, Sm covers S. Now observe the following. As you can see here, what are the properties of Qm? Qm here is closed. Why is closed? Because S being a closed set, and this is also closed. So finite intersection of closed set is closed set. So properties of Qm. Number 1, Qm is closed since it is the intersection of closed sets S and Rn minus Sm, because both S and Rn minus Sm, they are closed. Number 2, Qm is decreasing, because why it is decreasing? Q2 here you have S intersection Rn minus S2. Q3 will be S intersection Rn minus S3. But what is S2? S2 is I1 union I2. What is S3? Is I1 union I2 union I3. So it keep on decreasing. So Qm here is decreasing since the set Sm, since Sm is increasing. Okay, because S1 is equal to I1, S2 is equal to I1 union I2, S3 is equal to I1 union I2 union I3. So Qm is decreasing since Sm is increasing, I mean. That is, you can say that Qm plus 1 is contained in Qm. Okay, means Q2 is contained in Q1, Q3 is contained in Q2, is contained in Q1, and so on. Now Qm here, being a subset of S, they are all bounded. Okay, Qm here being a subset of S, it is all bounded. Why? Because S is bounded, and moreover Qm is also, it is closed, being the intersection of two closed sets. So now we can apply Cantor intersection because Qm here is closed and bounded. Now we can apply Cantor intersection theorem to conclude that intersection of Qm is not equal to phi. M here varies from 1 to infinity. That is there exists some x bar, okay, belong to intersection of Qm. M here varies from 1 to infinity. So this implies that x bar here will belong to Qm for all m. Whatever m you take for x bar will be a common element of Q1, Q2, Q3 and so on. So this implies that what is Qm here? Qm is the intersection of S and Rn minus Sm. Means the collection of all those points which lies outside Sm. Collection consists of all those elements of S which lies outside Sm. So this implies that x bar here will belong to S minus Sm, which means that x bar here will belong to Sm, but x bar does not belong to Sm for all m. Which means that there is some point in S. There is some point in S which lies outside. There is some point in S which lies outside Sm. And what is Sm? Sm is I1 union I2 union dash dash union Im, which is not possible. Why it is not possible? Because S here is contained in S1 union S2. That is, we can say that S is contained in union of S1, Sm, where m varies from 1 to infinity. What is S here? S is contained in union of I alpha. So alpha belong to indexing set I, means that S is contained in I1 union I2 union dash dash. That is obvious, which means that S is contained. What is S1 S2? S1 is I1, S2 is I1 union I2, Sm is this. So this shows that S is contained in union of Sm. So but what we have shown here is that suppose no Qm is empty, it means that this shows that there is some point, say x bar, which is in Qm but lies outside Sm, which is not possible because S is completely contained in union of Sm. So therefore this implies that S is contained in I1 union I2 union dash dash union I. Sm here is, what is Sm? Sm here is, we have defined it to be the union of first m natural numbers, say Ik. What is Sm here is union of Ik, where k here varies from 1 to m. So it is I1 union I2 union dash dash union Im, because what is Sm? It is union of Ik, where k varies from 1 to infinity. So therefore, why this contradiction arrives? Because we have shown that no Qm is empty. So this shows that there must exist at least some for some m Qm must be empty. Hence the proof, that is, every closed and bounded subset S of Rn is compact. So this is an important theorem, Heine borel theorem. They can ask you in the exam, means this question: assume F be an open covering of a closed bounded subset, closed and bounded set S in Rn, then a finite subcollection of F covers A. The proof will be the same. This is nothing but Lindelof covering theorem. The converse of this theorem also used to come, that is, if S is compact, then show that S is closed and bounded. That will discuss it in the coming days. Okay. So you just see this explanation. If anything is not clear, then you just let me know. Okay.